Hello, my name is Pascal Boulet. I'm a professor at the University of Lorraine in France, and today I will talk about the LASH fire project. There will be two parts for my talk. First, I will give you an overview of the project, and then we will have a focus on the tasks that are related to evacuation. Here is a slide that is simply taken from the LASH fire website, and that summarizes what we are doing in this project. LASH fire means legislative assessment for safety hazards of fire and innovations in rural ship environments. The objective of the project is reminded in the middle of the slide, and as you can see, the idea is to provide a recognized technical basis for the revision of the international IMO regulations and, of course, enhance fire prevention and ensure independent management of fires. What is really important for us is that we do not want only to provide some results regarding research and development. We want also to study the possibility of integration of board and also to check that the safety is improved on board thanks to the recommendations that we could do. This is a project that is supposed to last 4 years and which gathers 26 partners. You have here an idea of the work packages that are involved, the technical work packages regarding effective manual operations, inherent safe design, ignition prevention, detection, extinguishment, and finally containment. And as I told you before, there is also a work package dedicated to ship integration and a work package dedicated to safety assessment, with in particular a model for a risk analysis that should show that we can improve the safety on board. Here is a list also of the actions that are involved in each work packages. And we consider that we have, in fact, 20 challenges in this project. I won't go into the details of all the action, but again, you find the different work packages regarding manual operations, safe design, prevention, and so on. And in particular, today, we will discuss about WP11, the work package dedicated to containment, because safe evacuation is supposed to be studied in this work package. So the project involves system suppliers, research and development suppliers, regulatory bodies, ship integrators, and we also take benefit from the opinion of two advisory groups for the authorities and operators. Here is a detail regarding the work package dedicated to containment with 4 actions. One is for the division and subdivision of rural spaces. The second one is dedicated to ensuring safe evacuation. And of course, we will have some details about that later in the presentation. The third action is about rural space openings and the role of the openings. As you know, this is a very important thing because you may have some fire occurring in a rural space and then smoke will flow through the openings and may affect the life-saving appliances in particular. So this is something which has to be connected to evacuation and fire integrity. And the last action in this work package is dedicated to ventilation and smoke extraction. We have 2 main tasks involved in the action related to evacuation. The first is an evaluation of fire integrity to ensure safe evacuation, meaning that fire propagation is connected to evacuation in order to have some input data regarding the conditions for this evacuation. And the second task is to ensure second pass or second means of walk-off abandonment, especially in the case when the ship is returning to a foreign port. The method is based on numerical simulations. We consider different generic ships, and in particular, a RoPax and a Ro-Ro cargo. A vehicle carrier is also considered in the project, but not for the evacuation task, of course. The scenario supposes that the fire occurs in the ro-ro space, and then, of course, first of all, people should escape toward the LSA. And second thing, disembarkment must be ensured at least during 3 hours. And for this particular point, we have to couple the fire propagation, the fire situation, with the evacuation. And the third point is that safe evacuation must be ensured in case of a return to a foreign port. So here are some pictures taken from the simulation. On the left-hand side, you have the situation in a ro-ro space where the fire occurs in a truck and then can propagate from truck to truck. And this is a dramatic situation here where when no drencher is activated, but we have to consider this propagation in the ro-ro space. And then the fire can propagate to the rest of the ship. And so we are conducting some simulations of the heat, fire, and smoke propagation through the ship. And these are some input data that are given for the evacuation part, and we can build, we can simulate and produce some maps of the time required from any place in the boat, depending on the distribution of the people at the beginning, and then see what is the situation from time to time. So this was for the very short overview of the project. Now I will really focus on evacuation in the rest of the presentation. And again, this part was prepared for me by Anthony Collin, and you can, of course, contact him if you want further detail on the models. At the beginning, we were thinking to the different possibilities to simulate evacuation. You can find what we call a microscopic scale model, which considers, in fact, individuals, which consider agents, and conducted the simulation of all the paths of all these agents. This is what is done, for example, with Pathfinder or with the code EVAC, which is combined with a fire dynamic simulator. Then another solution is a macroscopic scale model. In this case, we consider a crowd. We consider a density of person per square meter. The problem of these two first scales is that the computational cost may become too important to conduct such a project as LASH fire. So that we rather considered a mesoscopic scale, meaning that the ship is modeled like a multi-compartment device, and we evaluate the time required to travel from compartment to compartment. The limitation is that the coupling is weak. I would not say that there is no coupling, but the coupling is weak with fire propagation. But at any time, we can have a picture of the position of the fire and then conduct a simulation that provides the required time to escape. Sorry. So I would not go into the detail of this slide, which was prepared by Anthony, because this is something related to the equations, but just to remind you that, again, the ship is, in fact, for us, a multi-compartment device in which, given a number of persons, are the input data, and also these persons are traveling from doors to doors, and two main input data are, in fact, the free speed of the people who are traveling toward the LSA, and also the maximal flow of person at each door. And for these important values, we used the prescription of the MSC circular in particular. Then, this is how we are working. We take the real ship, here in this case, the Stina Flavia. We have detailed maps we take detailed design of the ship, and we adapt it for our simulations in order to study for every deck, for every compartment, what is the required time for evacuation. What we obtain is such kind of result. You have in the middle of the slide the number of people as a function of time that are reaching the LSA, so that you can see that after 183 seconds of travel, every people in the ship may theoretically join the LSA. Considering the reaction time that is prescribed, which is 300 seconds for a daytime scenario and 600 seconds for nighttime scenario, you have the escape time, what I would say, which is the escape time at the very beginning of the fire. What is also interesting is that we can have some other data regarding the number of people leaving a given doorway. We can observe what are the main doors that are used by the people. And this is important for us in order to identify some weak areas that could be dramatically affected by the fire and that may penalize the evacuation. And we can also compute the number of people waiting behind the door as a function of time, which is the second graphic here. And some doors are particularly critical. And then we see as a function of time how many people are waiting behind the door because of congestion situation. This was a particular simulation for the Stina Flavia with these input data here and considering 466 passengers, considering some data provided to us by the ship operator, in fact. Then what we did was to put some penalties in some part of the ship, considering, for example, that at this place, which is a very important door for this deck where all the passengers are, then if a fire occurs here, this door can no more be used and people have to find another path. And these are also two important places because here you can find some stairs towards the upper deck where the restaurant is situated, and this restaurant is the life-saving appliance. So that we can compute again the new situation and find whether or not the time is affected by a possible weakness on this area. But in this particular case, you can see that the total travel duration is now 185 instead of 183 seconds. So very limited impact. This is not exactly the same for this stair here. If it is affected and if people have to find another way, some more time will be consumed in order to allow all people to find a way toward the LSA. But again, consider that this is only an increase by 40 seconds, whereas the total time, considering also the reaction time, is something like 483, if I remember, and 783. So this is not something that we find very dramatic situation. This is not really a crucial weakness, I would say, regarding fire integrity. What we did also is to test another situations where we could, for example, improve the travel by enlarging some parts, some doors or some corridors, and we produced some results where we see the relative variation of the traveling time as a function of a relative enlarging of the doors and the corridors. But again, it seems to us that the gain is not so much important because what is really guiding the total evacuation time in this first situation of escape is above all the reaction time. We also conducted some simulations by considering some variations of the number of passengers. Of course, this is a kind of sensitivity study, and in particular, we wanted to see whether or not by reducing the total number of persons, for example, there was something to gain in terms of evacuation time, but not so much considering the results that we got. And as a conclusion for the moment, at this stage of the project, but keep in mind that the LASH fire project started only 1.5 years ago, what we have done is to prepare a fire propagation model and an evacuation model. We applied it on the Stina Flavia, and we are ready to apply it on the Magnolia Seaway, and the second ship. We are able to predict some escape time to identify possible weak areas and test the fire integrity on this location. And what we are currently doing now is to prepare some recommendations for the ship design if needed. I mean, if we prove that it has a huge effect really on the evacuation possibilities, something like enlarging the stairs or the corridors, or something like creating new escape routes, for example. And we will also have to provide some recommendations regarding the fire integrity and the improvement of the fire integrity, especially in the weak area that we will identify. And the last part, and we are already working on it, is to evaluate alternate evacuation paths and to find solution, especially in the case of a return to a foreign port. So thank you for your attention. Of course, you may contact myself or Anthony, who is the leader, in fact, of this task dedicated to evacuation. And don't hesitate if you have any question. Thank you very much for your attention.